Hello there and welcome to my channel on chemistry lessons. Please make sure you like and subscribe to make sure that you don't miss out on any future content that's going to be uploaded.
So this video is all about the term entropy. So we're going to start off by looking at what it is, and then we're going to move on to how we make predictions for any entropy changes during a chemical change, chemical reaction. We're also going to look at how we calculate entropy changes given data. Okay, now this is quite an advanced definition for entropy, and it isn't one that we would use at A level, but it's a measure of the amount of energy that's unavailable to do work within a closed system. Now those of you that have seen the videos on enthalpy will see how it's a slightly different type of energy. So the idea is that it's a different type of energy to enthalpy. We don't need to worry too much about this definition, and we're going to use the term disorder or randomness to describe entropy. So we're going to stick to these two definitions. It's a measure of the disorder or it's a measure of the randomness, and it's a type of energy. And instead of using entropy, we're going to use the symbol S, because S is going to denote entropy. And when we see this triangle S, this is actually a symbol delta. So this means delta S, which means change in S, which means change in entropy. For example, in enthalpy reactions, you'll see delta H, which is change in enthalpy. So we're going to be focusing now on the change in disorder or the change in randomness of a chemical system. So to try and clarify these terms, disorder or randomness, and again, I'm now going to get rid of randomness and I'm just going to use the term disorder. You can use the word randomness. I'm going to stick to disorder. Now, easiest way for me to explain this or try and describe this is to think about the particle model, which you might have done a long time ago in science. I here in front of me have got the particles in a solid, the particles in a liquid, and the particles in a gas. Now if I was to ask you to put them in order of disorder or randomness, hopefully we'll agree that the most disordered particle arrangement is a gas, because they are moving randomly in all directions. It's quite difficult to predict where those particles are going to be. A liquid is definitely more ordered than a gas, so we'd say it has less disorder. So the entropy of a liquid will be less than the entropy of a gas. Likewise, when it comes to being solid, those particles are very ordered and therefore have a low disorder, so they'd have a low entropy. So we're making a link here between states of matter and a measure of entropy, and therefore we're making a link between temperature and entropy. Because if you think about a substance, as you heat it up, so let's think about a solid, let's think about absolute zero. So an absolute zero is 0 kelvins, and in theory that's when everything is perfectly ordered. There's no entropy whatsoever. So the measure of disorder is 0 at 0 kelvins, because there's no movement of any particles. Everything will be a perfect lattice, everything will be solid and perfectly ordered. There'd be no vibrations of any of these atoms. As soon as you increase the temperature though, these particles in a solid will begin to vibrate and become more random, more disordered. And as you continue to increase the temperature, eventually it will melt, and there's a significant jump in disorder, because suddenly these particles are able to move around in a liquid. So in the liquid state, these particles can move, which is significantly more disordered than a solid. So we have an increase in entropy. And if we continue to increase the temperature, eventually a substance will boil once it reaches boiling point. And at that point, these particles are completely disordered. They're moving freely of each other, randomly in all directions. And if we continue to increase the temperature of that gas, then those particles will move faster and will be even more disordered. So there's a direct link here between temperature and disorder. Okay, so let's look at how we can represent an entropy change on this graph in order to show how entropy changes with temperature. Now this on our x-axis is temperature, and it's in kelvins. The lowest possible temperature is 0 kelvins, that's absolute zero, which is minus 273 degrees C. And on our y-axis we've got entropy, S. More on the units later. But at absolute zero, there's no disorder. Everything will be perfectly ordered. It doesn't matter what this substance is, it can be anything. In theory, at absolute zero, everything is a solid and everything is perfectly ordered. There's no disorder at absolute zero. So we must start at the origin, and it doesn't matter what this substance is. And again, once we increase the temperature, no matter what this substance is, it will eventually melt. Some things will melt at higher melting points than others, but eventually it will melt. And again, continue to increase the temperature, eventually it will boil. And again, some things might boil at much lower, like significantly lower temperatures, other things might be thousands of degrees. Now, so what's going to happen is, we're going to start at the origin at 0, 0. There'll be a steady increase in entropy, even whilst it's a solid. So during this entire phase, it will be a solid. And between these two temperatures, it will be a liquid. And above this temperature, it will be a gas. So we're going to have a steady increase in disorder. Nice steady increase. When it melts though, we have a jump. So it will jump in entropy during melting, because we know the liquid is significantly more disordered than the solid. And this is a measure of the disorder. And again, the liquid will slowly increase in disorder. And then as it becomes a gas, we have quite a significant jump here. And then once again, if you increase the temperature of a gas, the disorder increases. Don't pay much notice to my gradients here. I can see that actually for some reason I've got different gradients. Don't worry about that. The key points are that we get a steady increase. When it melts, we get a significant jump. And then when it boils, we get an even bigger jump. So actually the fact that this arrow, number 2, is bigger than number 1 is quite important, because the difference in disorder between a solid and a liquid isn't as big as the difference in disorder between a liquid and a gas. Let's remind ourselves, gases are the king of randomness. They are the most random state. Then liquid, and solid is the most ordered. So we can represent this change in entropy for any substance would have that shape. Steady increase, big jump, steady increase, an even bigger jump, and then a steady increase again. So this allows us to make fairly accurate predictions about entropy values just using states of matter. So if we can see that something's a gas, we can make a fairly comfortable prediction that it has a high entropy value. So it's got a high level of disorder. And if we were comparing that to something that was a solution or a liquid, we'd be able to predict that the gas has a higher entropy value. For example, comparing oxygen gas to liquid water. And likewise, if we then looked at something like sodium chloride solid, we would predict that the solid had the lowest entropy, the liquid, and then the gas. We can put them in order of entropy values, just based upon their phases. However, what do we do if we're asked to compare the entropy of two gases, for example? So here they're in the same phase here. We've got two gas molecules, hydrogen and oxygen. Right, well, let's have a think about this. Let's try and make sense of it. So oxygen would be an O2 molecule and hydrogen is a H2 molecule. They're both gases, they're both fairly disordered, they're both going to have high levels of disorder, they're both moving randomly. But which one is more random? I am very confident that I can predict that the entropy of oxygen is greater than the entropy of hydrogen, provided they're at the same temperature, of course. Now, the reason I'm saying this is because an oxygen molecule is bigger than a hydrogen molecule. It has a bigger MR. It's got more electrons, it's got more protons, it's got more neutrons. Okay, it's a bigger molecule. So we can make a link between the MR of a gas and its disorder. So a gas with a bigger MR will have more disorder than another gas of a smaller MR. So we're making a link now between the MR and entropy. Okay, so using this knowledge now, we're going to make some predictions on some following changes. So let's have a look. Let's take sodium chloride solid becoming sodium chloride solution. So let's make a prediction on the delta S. Now, when we see an aqueous, that means it's in solution, it's dissolved. So instead of seeing NaClAQ, what we should be seeing is in fact 1 mole of sodium ions and 1 mole of chloride ions. So what we're actually seeing is 2 moles of ions. Okay, so what we have on the left hand side, we have 1 mole of ionic lattice, 1 mole of solid. On the right hand side, we have 2 moles of ions. Now let's think about the disorder. 1 mole of solid or 2 moles of aqueous ions. Aqueous ions being in solution, being able to move. They have a much higher disorder than 1 mole of solid. So our prediction here would be that delta S is positive. This would be a positive, an increase in disorder, hence a positive delta S. Let's take a look at the next example. We're going to have copper carbonate solid becoming copper oxide and carbon dioxide. You might recognise this as the thermal decomposition. So what's happening here? We've got 1 mole of solid on the left. This isn't too clear, this is a solid, this is copper oxide, is a solid. So we're going from 1 mole of solid to 1 mole of solid, 1 mole of gas. Now, gas, remember, is the king of disorder. So as soon as we can see that a gas is being made, we've got no gas on the left hand side, so we've got no gas. But on the right hand side, we do have 1 mole of gas. That's going to be a massive increase in disorder. So gases are going to drive this. So the first thing we should do is count the number of gas molecules on both sides, because that's going to be the driving force. No gas molecules, 1 gas molecule. That's going to be an increase in disorder. Therefore, delta S is going to be a positive change there. Let's take a look at this one. 2O3 becoming 3O2. So this is ozone, O3. We've got 2 molecules of O3 becoming 3 molecules of O2. But the thing that I'm most interested in is the state symbols. We've got 2 moles of gas on the left and 3 moles of gas on the right. 3 moles of gas is more disordered or more random than 2 moles of gas. So we're going to again see an increase in disorder. My explanation is because we've got 2 moles of gas becoming 3 moles of gas. 3 moles of gas is more random than 2 moles of gas. Therefore, delta S is a positive change here. Let's have a look at this one. So again, let's focus on state symbols. Now, all four are gases here. All four substances are gases. On the left-hand side, we've got 9 moles of gas, or 9 gas molecules. On the right, we've got 10. So we're going from 9 to 10. That's more gas molecules in the products. That's going to be more random or more disordered. So again, we are seeing a positive entropy change here because we are seeing an increase in disorder. The products are more disordered than the reactants. Next one then. So let's have a look at this change here. So the first thing we have to look for are state symbols. So let's take a look at the state symbols first off. Aqueous, aqueous, solid, aqueous. So the first thing I notice is there's no gases involved here. So unfortunately the king of disorder is sitting this one out. But we do have quite a lot of aqueous, quite a lot of solutions. So what we need to do is we need to visualize these solutions as their ions. So instead of seeing 2KNO3, I'm going to see 2K plus and 2NO3. Remember, be careful here because it's 2 NO3s, 2 KNO3s, that means we've got 2 Ks and 2 NO3s. So this right hand side here is 1 mole of solid and 4 moles of aqueous. That's what I've got on the right hand side. So how does that match up against the left hand side? Okay, left hand side we've got our 2K plus aqueous from the K2SO4. That also contains an SO4, 2 minus aqueous. So K2SO4 contains 3 aqueous ions. BaNO3, that contains a barium ion and a nitrate ion. So the left hand side contains 1, 2, 3, 4, 5 moles of aqueous. So the left hand side is going to put 5 moles of aqueous and the right hand side is 4 moles of aqueous and 1 mole of solid. Remember, aqueous would be in that liquid phase. It's moving around. So aqueous is more disordered than solid. So my prediction here is the left hand side is going to be more disordered than the right hand side because we've gone from 5 moles of aqueous to 4 moles of aqueous and a mole of solid. So the right hand side is going to be more ordered and therefore we have 5 moles of aqueous becoming 4 moles. That's going to be less ordered, so we're going to have a decrease in entropy here. So this would be a delta S would be a negative change. Okay, it's probably worth pointing out at this point that the number of moles don't have to match on both sides. It just so happens that this example's gone from 5 to 5. Doesn't have to be the case. Okay, magic. Okay, next question then. Let's have a look at this one. So we've got H2 gas plus I2 gas becoming 2HI gas. So the king of randomness is back. The gases are back. Okay, so I'm going to have a look here, and on the left hand side we've got 1 mole of H2, 1 mole of I2, or 1 molecule of H2, 1 molecule of I2. So that's 2 molecules of gas on the left, and it's becoming 2HI. So that's 2 molecules of gas on the right. So this is really difficult to make a prediction here because I've got 2 molecules of gas on the left and 2 molecules of gas on the right. So actually it is pretty much impossible for us to make a prediction here. We can't use molecular masses because the total mass of the left is the same as the total mass on the right. It's all gas. So if I was asked to make a prediction here, I'm unable. I'd say it's very close to 0. So I'd say delta S is going to be very close to 0 here. So what we need to do, or what we can do in situations like this, is we can actually quantify the entropy. So here we see in here standard entropy values for the 3 species in this equation. So we can actually quantify the entropy of the reactants and the entropy of the product. So let's do that. Left hand side is our reactants. So we can see that 1 mole of H2 has the entropy of 131.0, and the entropy of I2 is 261.0. Let's add them together and we have the entropy of our reactants. 131 plus 261. So the entropy of reactants is 392 joules per Kelvin per mole. And for our products, we've got 2 moles of HI. We can see 1 mole of HI is 206.6. So we've got 2 times 206.6 is 413.2. So we can see here that the entropy of our products is greater than the entropy of the reactants. So delta S is plus 21.2 units joules per Kelvin per mole. So we've actually managed to quantify it there by working out the entropy of the reactants and the entropy of the products, and we've added them together depending on their molar quantities. Okay, so it's time now for you to have a go at a question or a past question. Okay, so what I suggest you do is I suggest you pause the video, you have a go at this, and when you're ready to go through the answer, you unpause the video. So I'm going to split this into 2 halves. I'm going to work out the entropy of the reactants and the entropy of the products, and then I'm going to look at the difference between them. So reactants is 1 times 50.2 plus 2 times 5.7, that's carbon, and then 2 chlorines, 2 times 2, 2, 3. So I'm just taking the information from the table. I'm going to add those together on my calculator. So 50.2 plus 5.7 times by 2 plus 2 times 2, 2, 3. I get a total sum of 507.6 joules per Kelvin per mole. Check your units. So that's the total entropy of my reactants. Now let's find the entropy of the products. I've got 2CO, so that's 2 times 198, and I've got 1 TiCl4, which is 1 times 253. Add those together. .649, same units, joules per Kelvin per mole. So we can see there's been an increase in entropy, but by how much? Let's find the difference between those 2 numbers. So delta S is plus 141.4 joules per Kelvin per mole. I've been asked to use the appropriate number of significant figures. The appropriate number here, I'm dealing with 33333. So the appropriate number is 3 significant figures. So my answer is in fact plus 141 joules per Kelvin per mole. Now what I would suggest you do now is to double check your calculation. If I was in an exam, I would use my calculator and double check that, but also I can make a prediction. If I look at the equation, I'm going to make a prediction. We've got 2 moles of gas on the left and 2 moles of gas on the right. So So that's not helping too much. However, I've got a liquid on the right. I've got 2 moles of gas plus 1 liquid. Where on the left, I've got 3 solids. It would be a fair assumption that 2 gas and 3 solid versus 2 gas and 1 liquid, the 3 solids and 1 liquid is going to be a bigger entropy. So I'm happy that this is an increase in entropy. Wasn't such an obvious prediction, but I would have predicted a positive delta S because we're making liquid and gas from gas and solid. So now it's time to step back a little bit and let's look at the bigger picture. So delta S is the entropy change. S is a measure of the disorder. And we've seen the units a couple of times. The units, because it's an energy, it's joules. But this one is joules per Kelvin per mole, not just joules per mole. It is directly linked to per Kelvin. So joules per Kelvin per mole. If you were to use joules per mole per Kelvin, same thing. It doesn't matter. Okay, just usually you'll see textbook as joules per Kelvin per mole. If you want to use joules per mole per Kelvin, so be it. Doesn't matter. Right, so bit of a summary then. Delta S can be positive. Now in terms of thermodynamics, that is seen as a favourable change. So an increase in entropy is a favourable change. Smiley face. And therefore, a decrease in entropy is seen as an unfavourable change. Okay, and that's in terms of thermodynamics. That's kind of our bigger picture of thermodynamics, which doesn't include just entropy, it includes our enthalpy. And if you look at future videos, you will see that we start to introduce the Gibbs free energy equation, and that's where delta H and delta S will come together. Okay, so make sure you look out on those future videos. Okay, let's have a summary then. What are the key points from this video? So the key points are that entropy is a measure of the disorder or randomness. The entropy or the disorder, randomness, increases with temperature. We've used states to explain that. It also increases with MR, provided the temperature is the same or the states are the same. So it increases with MR. We can predict delta S, whether it's positive or negative, so we can make a prediction if we think it's going to be positive or if we think it's going to be negative, using number of moles and states. Remember, the gases were the kings there. We could quantify delta S, we can calculate it by finding the total entropy of the reactants and the total entropy of the products and working out the difference. Units of delta S are joules per Kelvin per mole or joules per mole per Kelvin, same thing. It is not going to be kilojoules per Kelvin per mole. Okay, we could measure it in kilojoules per Kelvin per mole, but be careful because 9 times out of 10 in your questions it's going to be joules per Kelvin per mole, not kilojoules. That'll be important later on when we start to do further calculations. And finally, a positive delta S is seen as a favourable change in terms of thermodynamics. So positive delta S is favourable, negative delta S is an unfavourable change. And that brings this video to an end then. So hopefully you found this useful. If you do, make sure you let me know in the comments and look out for future videos. Thank you.